Okay, let's talk about how to find unit normal vectors to a surface. So in the previous video, I mentioned that we'll be considering surface integrals where the integrand is going to look like f dot ds, where ds is shorthand notation for the normal vector times the surface area element. And this roughly corresponds to the fact that whenever you have a surface, each of the areas is associated with a normal vector. So you can actually think of this as kind of like an area vector in some sense. And this necessitates the question, though, what and how to get that uninormal vector. How do you actually construct this thing if you want to evaluate integrals of that type? Well, just like if you go back to the one-dimensional case, which is always helpful to see some stuff, if you have a tangent vector to a curve, then the normal vector is going to be orthogonal to that curve, right? That's just a way of saying that the normal vector times the tangent vector, or dot product, is 0. Well, in the surface case, it's identical. It's very similar. So the idea is that the normal vector dotted with tangent vectors is equal to 0. In other words, the normal is orthogonal to the tangent. So all we need is to get two tangent vectors because we actually have a nice procedure to get orthogonal stuff. So we can actually construct this thing using a cross product. Right, because if we have A cross B, this is actually perpendicular to both A and B. Right? So all we need is two tangent vectors. And then we just cross them. And that gives us our normal vector. We need to make it a unit vector, so we'll divide by some constant, but that's the idea. So how do you get two tangent vectors? Of a surface. Well, notice the numbers, the numerology here. Two tangent vectors, and a surface is 2D. So that means it's like a function of two variables. So you can almost just taste the fact that we're going to have to take derivatives. So in fact, RU and RV are exactly the tangent vectors that we want. And of course, I'm using lazy notation. This is the partial derivative of our surface parameterization with respect to u and v. And of course, what do I mean by surface parameterization? This is just, we have x, y, and z coordinates, which are functions of dummy variables. This could be spherical, this could be cylindrical. This also could just be graphical. For example, if we use curves, it could be x, y of x. We covered this in a previous video, but that's just the idea of what's going on here. So why are these things tangent vectors? That seems awfully easy. Well, it turns out, if we draw this pictorially, there's an easy way to see this. So what we'll do is we'll increment our position vector by du. And so we'll end up with a new vector, r, and I'm going to abbreviate this as u plus du. There's actually v, but I'm omitting that dependence to make this clear what's going on. So the displacement is what we're looking for here. The displacement is approximately u times ru. And this is by the mean value theorem or Taylor expansion. Okay? And so we can do the same exact thing with v. And so our displacement vector in this case will look like v times r sub v. So our displacement vectors ru and rv, notice that they transfer r to another r. So in other words, they stay, r stays inside the surface. And so this is important because this is exactly what tangent vectors should do. They should displace vector. They should keep your vector inside the surface. In contrast, normal vectors push outside the surface, right? Because if you have a normal vector, and that's your displacement vector, surely it'll be pushing your vector outside. You can think about this also from the curve point of view. So if we have our point, we have a normal vector, then if we actually are displacing, we'll get a vector that's outside of out of our curve. But in contrast, if we now displace to another point of the curve, so if we look at r of t plus dt, then our displacement vector, using Taylor expansion, is dt times r prime of t. And notice how it stays inside the curve. So that means that r prime of t is a tangent vector. Okay, so it's just it's analogous to the curve case. So these are our two tangent vectors. So in fact, now we get our normal vector. It's just tangent cross tangent. Okay, so that means if we take our ru cross rv, and then we put some normalizing constant, then this thing is now a unit normal vector. And that C, it needs to satisfy, it's a unit vector, and it also needs to have a good orientation. So it'll have an outward orientation for example, closed surfaces. For these things, you can think a sphere. You can think a cylinder with a top and a bottom. And so our unit normal vectors will look like this if they're outward. So that's what the outward orientation means. The only reason I'm mentioning this is because if you compute RU cross RV, it might have the wrong orientation. So now just add a negative sign, if that happens, and that'll be encapsulated in that C that's in front. So in other words, our normal vector will be plus or minus our cross product divided by its length. And that dividing by this makes it a unit vector. Okay? And we might use some other orientations, like if we have an open surface, something like this, like a bag. We might use something like we might use a plus, but I'll get to this when we actually need bags. Right now, we'll just use closed surfaces. So let me just go over real quickly. How do you actually get some of these normal vectors and just check that we have the right orientation? So again, my favorite surfaces are spheres and cylinders. And I suppose we can also include boxes, but boxes are kind of easy. Well, let's start with boxes. So how do you get that normal vector? Well, I mean, you can just draw it. It's the remember, it's the outward. We're always doing outward. So I'm just going to draw that normal vector. For a couple of these. And to make the box concrete, let's just do the unit box. So how do we get that normal vector? Well, in this case, it'll just be look. In this case, for this side, I think it'll be 1, 0, 0, because it'll just be the standard basis vectors, right? You'll just use your I, your J, and your K, and you might put a negative sign wherever you need it. Right, like let's just look at the XY plane for concreteness. So here I would use minus J, 0, 1, 0, and I'll put a negative sign there. And here I would use 0 plus 1, 0. Here I would use 1, 0, 0, and then finally you would have a negative sign. Okay, and how does this follow from RU cross RV? Well, I mean, for this obvious example, I wouldn't even do that. But if you really want to see it, then let's do this right. Let's do this face here. So this face is x equals 1. That's the surface. So now our parameterization is R of the free variables, which are y and z. Well, it's just x, y, and z with those coordinates. You should do nothing. So 1, y, and z, our y is 1. I'm sorry, 0, 1, 0. Our z is 0, 0, 1. But that's just j. That's just k. So ry cross rk, I'm sorry, rz, this is j cross k. That's I. And remember, if you're crossing unit vectors, you just use cyclic. You go cyclic. Okay, so that's just what we get for the normal vector. So let's move on to something actually non-trivial. Okay, let's go with a cylinder. Okay, so how do we get the normal vectors for this cylinder? Actually, for this, I like inspection. I like just looking at what they are. I think you can get away with that. So you can see there's 3 cases. You might call this surface S1, this is S2, and this is, you might call this SC, the cylindrical part. And for S1, I think K, I think that has to be clear, right? Because this is like Z equals, for example, this could be Z equals 1. This could be Z equals 0. And for S2, I think we're going to use minus K for that, right? Again, it's outward, so that's why. So really the only non-trivial part is SC that we need to think about. And how do you do that? Well, by inspection, let's just see what we should get and let's see if it works. It looks like if we do the xy plane and we just look at that circle, the normal vector should look like this, right? This is actually xy. This is the same direction as xy, just the position vector. So actually, I would suppose that the normal vector would be proportional to x, y, 0. Notice that there's no z component, right? Because if there were, it would be pointing up or down. So, is our candidate, is it orthogonal to tangent vectors? If so, then that's good enough, right? We don't need to do that cross product. This is a totally legit way to do it. So what are the tangent vectors? Well, we need our R, parameterization. So I would just use cylindrical coordinates. So let's just make this concrete. This is a cylinder. Let's say x squared plus y squared equals a squared. So x equals a cosine theta. Y equals a sine theta. So R will be a function of 2 variables, theta and z, which is free. So our R theta, as usual, will be minus a sine theta plus a cosine theta. RZ will just be 0, 0, 1. So let's just check really quickly that the normal vectors dot r theta and rz are equal to 0. So our candidate normal vector, of course, was xy, 0. Remember, it's always proportional to, because we have to make it a unit vector. So if we now use that x is a cosine theta, y is a sine theta, then what we're doing is now we're going to take a cosine, a sine, and we're going to dot it with each of these things. So this is minus as, and this gives us a squared c times minus s plus a squared s times c. Obviously, this is 0. And similarly, with our z part, that's also 0. So therefore, n, it's going to be plus or minus xy divided by x squared plus y squared. So now which one do we choose? Do we choose the plus or do we choose the minus? I think the plus is clear, right? we should choose that plus sign because it's the outward normal vector. So we choose that plus sign. So let's just do the sphere one really quickly. So the outward normal vector will look like these, and drawing inspiration from the cylindrical case, surely the normal vector will be proportional to the position vector. So that means surely it should be something like r divided by its length. And I think it's going to be the plus sign, right? Because if I reverse the sign of one of these vectors, it would point inside, and we want the outside, outward pointing vector. So that's my claim. I'm claiming this is the uninormal vector. It's just the position vector divided by its length. So let's check. So we just need two tangent vectors. So we need R parameterized. I would obviously use spherical coordinates to do a sphere, right? What else do you expect? So R in spherical coordinates, well, first of all, we have our x and y. I'm going to use this kind of notation I introduced a while back because this kind of helps me. And if we go back to our usual diagram, then we plug that diagram in, and we should get something like sine phi and then we'll have cosine phi on the other side. Okay, so let's just take the derivatives. And I'm going to do us all a favor, and I'm going to abbreviate some of these things. Cosine and sine. So now let's take the theta derivative. So the SV will do nothing. This will become a minus sine. This will become a plus cosine. That'll be a 0 because we're differentiating theta. And we can do the phi in a similar way. Okay, and then finally our normal vector will be in our spherical coordinates is actually just r divided by its length. So it'll actually just be this thing that we have right here. So it'll actually just be r. So let's compute this. The normal vector times r theta. Okay. It looks like we'll get s phi squared. And then we'll have the dot product of these two vectors here. That's 0. And then finally we have the last term. And that's also 0. So let's finally conclude with, and let's just check that that last dot product is 0. So if I match these cosines and sines, and then I take the dot product of these two vectors, we get something promising. And so then I'll match these last two terms. So it looks like this is 1, and looks like this will cancel and give you 0. So therefore is the outward unit normal.